Now we know the magnetic force exerted by a magnetic field on a moving charge. So recall, the magnitude of the magnetic force is equal to the magnitude of Q times V sine phi. Okay? And we also know the direction of the magnetic force is given by either using the right-hand rule or the cross product. So if we try that here, so suppose we have a uniform magnetic field B and a charged particle, say a positively charged particle Q is moving in this direction. So this is the direction of the velocity, and it enters this uniform magnetic field. So once it enters the magnetic field, then it will experience a magnetic force F, and if we check using the right-hand rule, using V, and we have the direction of the magnetic field is negative Z in this case, and then you have the magnetic force, which is upward. So the question now is, what happens to the charge as it travels in the magnetic field? So how would it behave? So take note that, well, from Newton's laws of motion, whenever a particle experiences a force, then it will accelerate. But in this case, the force is acting perpendicular to the velocity. So that means that there will be no change in the magnitude of the velocity. So that the speed of the charged particle as it moves through the magnetic field will be constant. On the other hand, because the magnetic force is perpendicular to the velocity, then the direction of the particle will change. So therefore, when it enters the magnetic field, it will not be able to keep the original direction. So what will happen is that it will be deflected. So it will be deflected this way. Okay? So recall centripetal force. So the magnetic force will act like a centripetal force, and therefore the particle will be deflected. So now the particle is here. Okay? And at this point, the direction of the velocity has changed. Now it's directed this way. Okay? And if you use the right-hand rule, the magnetic force is perpendicular to the velocity. So the magnetic force now is directed this way. Okay? And then that means that it cannot keep this direction. It will be deflected again. So it will go here. Now our particle is already here, and that means that it is moving upward. Okay? And that means that the magnetic force now is directed this way. Just keep in mind that the magnetic force is always perpendicular to the velocity, or if you're confused, then just use the right-hand rule. So the velocity is upward, magnetic field is still into the board, and the magnetic force is directed this way. So then it will be deflected again. So you know where this is going. Now the charge is already here. Okay? And it looks like it's making a U-turn, and the direction of the velocity is now here. So the magnetic force is directed this way. Okay? And therefore it will be deflected again. And finally, the charge will exit the magnetic field. Now, let's summarize this. When a charge Q moving with the velocity enters a magnetic field, it will experience a magnetic force perpendicular to the velocity, which will deflect it back. So it will make a U-turn. Okay? And the motion of the charged particle in the magnetic field is actually circular motion. As you can see here, well, this is only half a circle, so it's moving with a circular path, and it will take a U-turn. Okay? So, if the magnetic force, which is QVB sine phi, and we're assuming that we're considering the component of the velocity perpendicular to the magnetic field, So the magnetic force, maximum magnetic force, let us say is equal to QVB. Okay? And then this magnetic force is also the centripetal force, because recall in centripetal force, the centripetal force is always directed perpendicular to the tangential speed, or directed towards the center of the circular path. And if you look here, the magnetic force is directed towards the center of the path, so therefore the magnetic force is also the centripetal force. Now recall that the centripetal force is equal to mv over r squared, where r is the radius of the circular path. If we equate the two, so we have QVB equals, oops, sorry, my bad. This should be mv squared over r. Okay, so we have mv squared over r. Okay, so take out one v here and rearrange this. So r is equal to mv over qv. Okay, so this describes the motion of the charged particle in the magnetic field. First, the motion is circular, and the radius of the circular path taken by the charged particle in the magnetic field is directly proportional to the mass of the charged particle, directly proportional to the velocity, well, all other factors being constant. Okay? So, for example, r is directly proportional to m. All other factors being constant, if we compare, for example, a proton and an electron moving in the same magnetic field, then because a proton is more massive, then the path taken by the proton will have a bigger radius compared to the path taken by the electron. Okay? Well, expectedly, as the velocity of the charged particle increases, then r increases. So if the charged particle is moving faster, then it will just move in a path with a bigger radius. It's inversely proportional to the charge. So the greater the charge, the heavier the charge, the smaller the radius. And it's inversely proportional to the magnetic field. The stronger the magnetic field, then the smaller the radius taken by the charge is. Now, question is, what if the charge is negative? Okay. Now, if the charge is negative, you can still use the right-hand rule. What will change is the direction of the magnetic force. Okay. So, if let us say, for example, the right-hand rule, you can use this for positive charges moving in a magnetic field. Now, if the charge is negative, it still is the right-hand rule, but replace the direction of the magnetic force. It should be opposite. Or you could use the left hand. Okay? So, let's just do that. For positive charges moving in a magnetic field, use the right-hand rule. And if the charge is negative, then use the left hand. So, if we're going to use the left hand here, so take note that, what will happen? Okay, so like this. Velocity, magnetic field, the magnetic force is downward. So therefore, if this charge is negative, it will make a U-turn. It will be deflected by the magnetic field, but in the opposite direction. Okay? And the question is, another question is, what if the charged particle is already inside the magnetic field? Then if the charged particle is inside the magnetic field, then it will not be able to get out of the magnetic field. It will just move in a circular path inside the magnetic field, and the radius of the path is given by this equation. Now, knowing this, one application of this fact is when enclosing, there are materials which cannot be contained using a material container. Because, let us say, for example, the temperature is very high, and therefore any material container will just melt. So what they do is they create a magnetic container. Sometimes they call it a magnetic bottle. So what they do is, let us say you have a very hot material. So the hot material is electrically charged, and then it's made to move in a constant magnetic field. So what will happen to the material is it will just be moving around the magnetic field track. Okay? So as I mentioned last time, because the Earth has a magnetic field, then the magnetic field of the Earth shields the Earth or protects the Earth from electric charges coming from space. So if electric charges coming from space try to enter the field of the Earth, then they will just be deflected back. Okay? So now, so far what we have, so we have the magnetic force, magnitude and direction, exerted by an external field on a moving charge. And then, using this equation, we have the behavior of an electric charge inside a magnetic field. So the next lesson is we're going to apply this to a collection of moving electric charges. Therefore, we're going to apply this to electric current in a magnetic field. And that's where the excitement will begin.